Good morning, ladies and gentlemen. Welcome to my project presentation of Raspberry Pi based computer vision robot. In this project, I have developed a computer vision robot using Raspberry Pi 4. Before getting details to my project, I would like to present you some of the project background, the historical background of robotics in general. 1478, Leonardo da Vinci demonstrated his self-propelled cart concept, where he used a spring stored potential energy. When the spring was released, the kinetic energy created from the spring potential energy would move a robotic buggy. University of Berkshire in 1958 came up with the tractor B250 driverless tractor. 1969, Auto Truck of Hampshire demonstrated their bullet wire guided Ferguson 165 tractor. New Holland of Netherlands demonstrated their GPS guided autonomous tractor in 1995. As of 2018, the market was 45 billion worth. In 2020, there is 240 billion pound market potential. My robotic project is just a small part of this bigger picture. I have used computer vision sensor, webcam, and this is my only and one sensor in my robot. So here I provided some of the justification that why did I use the webcam rather than using its counterpart of reflection based sensor like IR sensors, sonar sensors, lidar sensors. The reason I used computer vision sensor is that it provides superior feedback through image processing. Then reflection based sensors contains higher number of information. Basically, in an image there is all the information, but it's just only matter of fact that how to extract those information and utilize them. Computer vision sensors has got many others positive sides, including it is cheaper. My vision sensor cost only £9, whereas its counterpart of lidar sensors, the cheapest one, is £70 to procure. It has got very low power consumption. I used only 12-volt battery, and it has got no moving parts, so it's less vulnerable for accident or any other kind of damage. Low power consumption, as I said earlier. This project is aimed at developing a computer vision based Raspberry Pi 4 robot. To accomplish this project aim, the following objective I have visualized in the form of this follow chart. I started building the cat parts at first. I have designed all the cat parts myself using Autodesk Inventor software. Then all the cat parts has converted to STL file format and transferred to the VRAP robot simulation software. Then on the simulation software, I executed my developed algorithm in Python programming language, where the virtual robot has got its own camera. Virtual robot with all the cat parts, it has got its own camera in virtual arena, and with the developed Python algorithm, it is possible to simulate the robot in virtual environment. When I have simulated my robot and all the bugs has been eliminated, and that means that I'm confident enough that it would work in real life robot, I transferred the code, little bit customization to the physical robot, and the same code, same webcam, but it is physical webcam, similar kind of feedback system compared to the virtual machines. Process chronology, I would like to discuss little bit more about the process I have already discussed. So these are the process of building the cat parts and the components used for this project. So the robotic buggy has got 4 wheels, 4 DC 6-volt DC motor, and Raspberry Pi 4 computer, and the motor controller. As you can see, the motor controller here, buck converter, 12-volt battery, and the webcam. I designed them all in Autodesk Inventor in CAD parts, and I converted them to STL file format, then transfer to the virtual robotics. Now the detection, next part in the virtual robotics, the following algorithm I have to develop: detection, recognition, global coordinates, and distance measurement. And when the program has been matured, I transfer them to the physical real life hardware. Background theory: to get my project working, I have to research a lot, and there are over 40 different academic sources I have utilized to come up with my project idea. So this is one of them I would like to discuss to you. So this idea was proposed by Lee and Hang, Taiwanese scientists, on their paper in 2013. So they used 3 input, 3 sensor: laser rangefinder, sonar sensors, aerial robot, and aerial robot. These are the sensors. They put input data, and the output is utilized by the ground station, and the hardware is the robot. It connects to the ground station. Station command the robot to move whatever to do with the feedback information it is getting from the 3 sensors. Next one is proposed by Wang and Silva, again another Taiwanese scientist, in 2009 on the paper. They proposed to use the Q-learning, reinforced learning, machine learning, for their robot to learn itself from its own mistake. So in this way, the robot, they would program the minimal program. They would give minimal instruction for the robot for problem solving, and the robot would utilize the Q-learning algorithm, reinforced learning algorithm, to learn itself from its own mistakes. Edge detection localization background theory is proposed by Yang, another Taiwanese scientist. He proposed that how to analyze the camera feedback information, camera analysis, how to do image processing for robotic movement to get the desired feature from that image. So it started with the input frame, grayscale. Then the grayscale image has been Gaussian blurred. After that, canny edge detection happened. Then object segmentation, Hoff transformation, and output frame resulting the desired feature has been marked for the robot to analyze that feature. Proposed solutions: analyzing all the academic sources, I have come up with my own solution for developing the algorithms. So I start with image acquisition from the webcam, then 3 stages of image processing happen: image pre-processing, main image segmentation, segmented image post-processing. Once the image has been post-processed, one image is ready for, once all the unnecessary things has been deducted from that image, then the image has been put through the feature extraction algorithm, feature-based classification. It has been classified what kind of object it is, application specific feature extraction. Then based on the robotic application, that feature has been utilized with other algorithms. Hardware selection: I have compared few of the single board computer in the market. So my justification was cost, efficiency, easy to program, on that easy to program, and frame rate per second for visualizing the image. So here are the few comparison against different neural network. So the ResNet, MobileNet, SSD, and SSD ResNet. These are some of the neural networks can work with a single board computer with a low computational power. And now, as you see, my choice of hardware is Raspberry Pi 4 because NVIDIA Jetson has got 36 frame per second. Raspberry Pi 3 is 1.4 frame per second, but the closest one to Raspberry Pi 4 has got 16 frame per second. And proposed hardware, I choose Raspberry Pi 4 hardware, and here are some technical specification of Raspberry Pi 4 hardware. It has got quad core A72 system on chip, Then the GPU is Broadcom Video Core VI, which is pretty much customized for machine learning operation, with the networking option of 2.4 gigahertz to 5 gigahertz 802 wireless LAN. The RAM, it has got 4 GB RAM with the Bluetooth interface, so this is very useful for robotic operation in IoT application. Programming interface I would like to discuss. I have used the Python programming language because it has got easy programming API, and also what I found is that with the recent learning trend in the market, in the industry, Python programming language has got a big potential to be a mainstream programming language. Also, it is really easy to code for anyone, easy to find the bugs. I used Spider 3 IDE integrated development environment with the Python programming language. The reason I chose the Spider 3 because Spider 3 has got the similarity with MATLAB programming interface, which I am more comfortable with. This is my VRAP robot simulation screenshot. As you can see, I have transported my robotic buggy to the virtual arena, and there is a virtual robotic cat on top of it in the arena, and the robot buggy can see with the onboard camera. The cat is visualized on the screen here. Now I have connected the VRAP robot simulation engine with the Python programming language, the Spider 3 IDE in node communication. Node communication is where multi-program in same computer or multi-program in multi-computer can communicate with each other and execute one or set of tasks together. So here I have used the IP socket to bridge the communication. So the first one is my IP address, the second one is the socket address, and the rest are some API framework. This is the schematics of my motor control circuit. I have used DRV8 4x2 dual bridge PWM motor controller. Basically, I have got 4 motors, so I have paired them. So there is a right side pair and left side pair. So one motor controller unit for the right side, one motor controller unit for left side. As my motor controller is dual bridge, so one controller can control 2 side motor same time with different code and input and output. Program design interface. These are the screenshot of the program I wrote to communicate with the VRAP program, and as you can see, this line of codes has been developed just to simply visualize the virtual camera image. So this is virtual camera. See the robotic dog in virtual environment. The libraries has been imported. So import VRAP, import NumPy, import matplotlib, import time. These are few of the libraries I have used to visualize the image. Then the buffering happened. The camera buffer has been converted to the still image. Then the continuous looping provide the video image. Motor control interface. Image feature extraction. Here you can see my physical robot, and at the bottom is some of the screenshot of what it is capable to do with the developed algorithm. You can see there is a red object, and the camera can localize where the object is. Here it is showing it is left, here it is showing it is right, and here it is showing it is in center position. With this line of developed code, HSB frame, CB to color, converting BGR to HSB, so RGB to HSB frame. Then there is a thresholding applied, low threshold, low rate threshold, and high rate threshold. So in between the low and high, the spectrum of the color coded image will only be accepted for the code, and other image feature is eliminated from the information. Then the marking happen. It put a marking at the center, and it also measure the distance from the camera, the object. Next line of code I have developed to measure the distance. So the first one was the location, left, right, or center position, and this one is for the distance measurement. So the robot can see the object in front of it, then it can analyze that it is in right location or left location or it in center position in compared to the screen resolution. Then it drew a bounding box, and changing the bounding box with the variable speed and distance, it measured the distance of the object from the robot to the bounding box. In this way, I have simulated what the robot is capable of. So I have drawn a wall with few of the bounding box painted on the wall. There is a red ball in front of it. This red ball is a moving object. So my robot would track this red ball and navigate against these red and white blocks. So as you can see here, it has tracked and it has detected the blocks, and it also detected the red blocks, and it has detected the location of the red blocks. Same time, it measured the distance of the red ball and the wall as well. Following algorithm happened. So the program initiated, then the object location has been analyzed. If the location is less than 1 and left, right pair will get activated. If the location is less than 1 feet and right, then the left pair will get activated for the robot to correct itself and keep the target in center position. Location greater than 1 and center, both pair wheel is clockwise. Location less than 1, left pair wheel is anti-clockwise. So this is a sharp turn from left and right. Then the end of the code program terminated, and reset and end happened. So those are the algorithms. Step-by-step algorithm has been developed with Python programming language, again with Spider 3 IGE. Convolutional neural network, artificial intelligence, has been applied to recognize different objects. So here you can see I'm holding a mobile phone, and my robot can recognize it's a mobile phone. It is me myself. It can see, it can detect and show that a person has been detected. Project outcome: the robotic guidance system developed is able to identify targets and navigate to it. It can identify the obstacles and navigate against it. When it is following the target, it keeps the minimum distance from the target just to avoid the collision. It follows a red blob and keep 1 feet distance away. It navigates against the wall. Here I have measured the distance of that red blob in real life with the measurement tape, and I have also measured with the camera with the developed algorithm. So as you can see, the camera is showing visualizing the image, and it is showing the distance of the image and the location. So the location it has detected is in central position, and the distance is 1.3 feet, whereas in real life it is 1 feet. I took a number of samples in this way and plotted a graph comparing the two value, the real life measured value and the camera measured value. As you can see, it is almost perfect. There are very slightly less error, but that also can be eliminated with higher level of signal processing. I used Microsoft Project for planning my project tasks, keeping track the progress, also any features I need to take a special care of. So as here you can see, I have initiated the project in 5 stages. So I started with initialization, planning, control, execution, closeout. So there are 5 phases. In 2 months time I worked in this tight schedule. There are some time deviation of the project highlighted in red, that I have to be repurposed the project task and reschedule it. So here it is highlighted in red. What I found is that Microsoft Project is really useful for planning a project. You can visualize all the project tasks with the interactive Gantt chart, and it has got an easy programming interface where you can go and change things as you need for the project to progress. In this project, the outcome I have got is field of advanced robotic has been explored. Python robotic capability explored, robotic hardware integration practiced, real life entrepreneurship option also explored. I'm also looking to maybe one day I'm also looking to commercialize my robot project based on how I'm gonna make it industry ready. Project conclusion, I would like to say the project aim and objective have been accomplished. A computer vision based robotic guidance system have been designed and deployed. Its performance have been analyzed and documented. Future works include lots of signal processing, make it perfect, make it deployable for real life industry. Thanks for attending. Any question?